Okay. Are there any questions or comments on last time's lecture? Okay. So, a couple of announcements. One is that the homework is due on Friday, and also the midterm is next Wednesday, so there's no class on Wednesday, October 22nd. At the time the class is, we're going to do the midterm. One more time, you can bring one sheet of 8.5 by 11 worth of formulas or whatever you want to write on it, two-sided. You can write as small as you want. The midterm does cover all the way through the end of the homework that you hand in this Friday. You're going to get the solution to that. Even though you're not going to get your graded homework back, you will, the exam covers all the way through FIR filters, window design, anyway. How many people have started the homework that's due on Friday already? How many people have finished it? Okay, very good. Okay, any questions or comments? Yeah. Can you use the mic, please?
The Chebyshev error that we find, I was going through the websites. They have different definitions at different places. Some places they say it's the maximum squared error. Somewhere it's the integral of the squared error. And some places it's the maximum error itself.
Is that part of homework?
Yeah.
And can you? I don't have the thing memorized. Tell me what the problem is, what the context is, so I can help you out.
So it's a different. So you find the filters for different kinds of windows. And then you find the Chebyshev error, and it says in brackets squared error for each of these filter designs.
And there's no definition of Chebyshev error in the book.
No, not that I think.
Dan, what policy should we adopt here? We should probably announce it. And
yeah, I put that on the website just last night, so it's posted. What you should be doing.
Okay, and what is it? Just so that I know.
Let's see, the way they did it before was the average of the squared error in the frequency domain.
Okay, thanks. There was one other question.
Are calculators allowed on the test?
You shouldn't need them, no.
Do we need a blue book?
It would be good if you bring a blue book, yeah. That way the sheets won't fly over and you won't lose some pages because your papers got lost or anything like that. That would be preferable.
What does amplitude response exactly mean? Is it just the magnitude of frequency response, or?
Actually, amplitude could be positive or negative. So it's just the real part of H of omega. Well, not real. Let's just go with the definition of magnitude of the frequency response, yeah. Okay. So you guys didn't have trouble downloading the MATLAB files needed to do the homework. You're using the MATLAB window function, and whatever the thing is, you're making regular progress towards doing the homework. Is that correct? Okay. All right, so let me get going with today's lecture. Are there any other questions or comments? Yeah, one more. Uh-huh.
There's a filter design toolbox,
Mhm.
and there's the command line.
Mm-hmm.
So the filter design toolbox does everything for you. You just click in a couple of
Oh,
places.
no, we didn't want you to have that. Right. That's the problem with MATLAB, actually, is ever since we adopted it, some of our previous homework assignments become obsolete because one button and the answer comes out. So don't use that. Any other questions or comments? Okay, so what I talked about last time was the idea behind window design, using FIR filter design using the window approach, essentially. And there was one question at the end of last time's lecture that sort of made me feel that I might not have explained this thing properly. This was one of the smart kids in the class who came to me and said, "What do you mean you convolve in the frequency domain? Why are you doing that? There was a bit of a confusion, but let me just, to remove that confusion, let me just explain what the fundamental idea is. The fundamental idea is you come up with an ideal frequency response. And many times that's a box-like function in the frequency domain, right? And what you want to do then is come up with the ideal impulse response. And again, many times that ends up being an IIR filter that doesn't even correspond to a rational transfer function. As example, if the ideal frequency response is a box, low-pass filter box in the frequency domain, the ideal impulse response in the time domain is a sink, which is an IIR filter, and it can't be approximated using rational transfer function in the Z domain. And then what we do is to make that finite, we multiply it by a window. We multiply it by another function, W of n, in order to get the impulse response of the filter we're interested in. And so what we spent time doing last time is trying to discuss various window functions, W of n's, that you multiply this thing by so that you end up getting your final FIR filter. And then somebody said, well, why are you showing convolution in frequency domain? Well, the reason I show convolution in frequency domain is not because of an implementation point of view, but just to show you, to make you understand, in the time domain, when I multiply my ideal impulse response by the window, what happens in the frequency domain. And what happens in the frequency domain helps us design better windows, okay? So essentially, in the frequency domain, the Fourier transform of the window function and the Fourier transform of the ideal impulse response get convolved. And the reason I showed that convolution is to convince you that the smaller the main lobe of the Fourier transform of the window function is, the smaller the transition width of the frequency response of the eventual filter. Remember, the final filter, just write it down here. So you start with h sub d of omega. That's no good either. Which is your desired frequency response. That's the thing that usually looks like a box. And then what you do is you take the inverse dTft of it, and you get, again, desired impulse response. And that's, again, something that, in this case, it would translate into a sinc function as a function of n. It's infinitely long. It's not only... Oh, okay. Could you turn...
This one not on or not?
I don't see a button here to push. Could you turn this on, please? Oh, you did it. Is it warming up? Yes, it is. Okay, thank you. Okay. Okay, so then you come up with h sub d of n, which is your desired impulse response, and then the final filter, this is the final thing you end up getting, is just h sub d of n times w of n, but this is just a window function. Okay? So this h sub d of n, most of the time, it's not only IIR, but it also does not have a rational transfer function. So that's really, as I said, that's doubly bad, because We all took DSP thinking that we can approximate filters that look like brick-like thing, like that, but in fact realizing those and implementing those in practice ends up being impossible. So what you have is, essentially what you're doing is multiplying this infinitely long filter by this window to make it finite duration. And this is the finite this is the final filter that we end up with. This is the thing that we implement. This is the FIR filter that we designed. Essentially, it comes from multiplying a desired filter with a sub-window function. And so the question that I got asked last time was, why are you looking at the convolution of the Fourier transform of that with this? The reason I do that is to understand the characteristics of h of omega, the characteristics of the final filter I end up designing, I have to understand the characteristics of Fourier transform this and characteristics of Fourier transform of the other one. In reality, I don't implement h of n in the Fourier domain. In reality, I just truncate this guy and I get 10 taps or 9 taps, and that's my h of n. But just so that you understand what happens in the frequency domain to this h of n, we went through that analysis, and what we showed is that so W of n has a Fourier transform, which is W of omega, and what we showed is that the thinner the main lobe of this guy is, the smaller the transition width of this filter is. Furthermore, the lower the side lobes of this guy are, the lower the ripples in this filter is. Who is that? Right. Okay. So that's why we did the analysis in the Fourier domain, and we looked at sort of convolving. I have the diagram here from last time, I think. That's why we did what we did last time. We're convolving. This is the desired thing. This is W of omega, and what we concluded is that the ripple. This is H of omega, the final filter. The ripple we get in the frequency domain is proportional to the side lobes of this, and the transition with delta of omega is proportional to the main lobe of this window function. And so that's I hope, is that clear to most of you? And then the other thing that we talked about is how do we design this filter? And what we found out with is that to control the main lobe, what are some knobs that we have? How can we control the main lobe? Well, there's the length of the filter, the length of the window. Sorry, tells you tells you the size of the main lobe width. The longer the window is, the narrower the main lobe width. Also, the shape of the window affects the main lobe width. And we also concluded to deal with side lobe height, the only knob that we have is essentially the shape of the window. In other words, the duration of the window, the size of the window doesn't affect side lobe heights too much. Side lobe height of this W of omega, this Fourier transform of the window. And so the conclusion that we reached was that the shape affects both side lobe and main lobe, and the size only affects the main lobe. And therefore, based on that, a good thing to do is to use shape to control the side lobe and to use size to control the main lobe width. And then I showed you a whole bunch of windows with different shapes, you know, the rectangular window, the Bartlett window, which is just triangular, then there's the Hamming, then there's the Hanning. One of those guys is called the raised cosine window, then there's the Blackman. And depending upon which one you use for a given window size, you get different main lobe width and you get different side lobe characteristics. And then we ended the last time's lecture with Kaiser window, showing that Kaiser sort of unifies all of these things in a nice way, in that it has a general form like this, where you have two parameters, beta prime and alpha. Alpha here is related to the length of the window. It's essentially alpha is equal to 2m, where 2m plus 1 is the number of samples in the filter. So parametrically, by changing alpha and beta prime, you can change the shape of the filter, and I showed you some examples of it. You keep the length the same, you change beta prime, and you get different behavior. You keep beta prime the same, change alpha, you get a different one. And what Kaiser did is and this is another point of confusion from last time's lecture, he came up with these design guidelines, okay, which is shown here. And somebody said, how did he come up with these numbers? 0.1102, 0.5428, you know, he only did that by running a million or billion simulations or numerical examples on a Kaiser filter, which is shown in this way. And then he fit curves through that numerically in order to come up with that. This is purely obtained in a numerical way. It wasn't arrived analytically, right? So what that means, he went to his filter here. He went to this filter and said, okay, I'm going to plot it for 100 different values of beta prime. I'm also going to plot it for 100 different values of alpha. So 100 times 100 is 10,000, or maybe he did it 1,000 times 1,000, a million. And then he computed these quantities, A, which is the 20 log 10 of the ripple, and delta omega, which is the transition width, and says, how are these two parameters related to alpha and beta prime? And numerically, he came up with this relationship. Yeah?
Just to clarify, it's the side lobe height that we're interested in, not the side lobe width.
Not exactly. You're right. Side lobe height tells you the ripple height. Main lobe width tells you the transition width. And why is that? Because of that convolution picture, right? If you think about this diagram here, this guy gets flipped over here, and as you drag it, it's the main lobe width that tells you what the transition width is. And then when it's not overlapping, the side lobe height tells you what the ripple height is, right? Exactly. So then what he did, I mean, just so that you know how he came up with it, as I said, he went to his filter, he tried, I don't know, 10,000 values of beta prime and 10,000 values of alpha, and for 10,000 times 10,000, that's 10 to the 8 filters or something. For all of those filters, he computed the ripple, which is minus 20 log 10 of delta, and he computed the transition width, and then say, how can I analytically or numerically relate these two quantities, delta of omega and A, to alpha and beta prime, and this is it. This is what he came out with. And so these are design guidelines. They're not 100% accurate. They're not precise. But you can use them to design your filter. And so we did an example where if you're given a certain set of specifications, like omega p for a low-pass filter, you know what the passband frequency is, what the stop band frequency is, what the ripple requirements are, then you can plug it into those equations and to get answers. Now, one deficiency of the Kaiser window design and FR filter design using Windows in general is that there's no mechanism in all of what I described to have a different ripple for passband than stop band. Coming back to Kaiser, he only has one number called delta. It's not delta sub S or delta sub P. And this ripple is, I don't know, the whatever ripple you get in passband, you can't, because in the frequency domain you're convolving the Fourier transform of window with your ideal filter, you don't have that much of a control to make the passband ripple be different from the stop band ripple. It is what it is, okay? There's not a lot of control. So as a result, Kaiser window design, or window design in general, doesn't give you the tools to have different ripple characteristics in passband and stop band. So when you're given a problem like that, to be sure that you satisfy the more stringent condition, you have to pick the smaller of the two, 0.001, as your ripple condition. Right? If you don't, you end up having 0.01 ripple in both passband and stop band, and that's no good. Right? Remember, the ripple condition is you want to have the amount of ripple in your passband and stop band to be smaller than some maximum level. Ideally, you want to have a brick. No ripple, zero, nothing. But reality, okay, you got to pick a number, and the number you pick is the smaller of the two, because if I pick 0.01, I might end up having 0.01 ripple in the stop band, and that I don't satisfy the specs. Anyway, so you get in WS, omega S and omega P, and so the ideal, that means that the ideal low-pass filter you want to design with H sub D of omega magnitude is 1 here, and 0 the rest. And where's a good value to pick for the cutoff? Well, we pick omega P plus omega S divided by 2, which is 0.5 pi. So that's our ideal filter. Now, the real filter, this is the magnitude response of the ideal filter. The real filter is going to have some phase response. And we can just say, look, we're going to stick to either type 1 or type 2. So that's the, so beta essentially is equal to 0. So this is the shape of our frequency response. So then you plug in, you compute delta of omega, which in this case is 0.2 pi. This is the transition width. You compute the A quantity, which is minus 20 log 10 of the ripple, which in this case is 60 dB because we picked delta to be smaller of these two. Plug it into Kaiser's two equations. That gives you beta prime equals to this value and m equals 37. Now beta prime has to be an integer, so we just round it up to beta prime equals 6. And after you after you compute alpha using Kaiser thing, you get m equals 37. And that means the number of taps of the filter is twice that. I'm sorry, it's 37 plus 1, 38, which in this case happens to be type 2. And that's not a problem because type 2 indeed can be a low-pass filter. If we were going to design a high-pass filter and you ended up with type 2, you're in big trouble. But in this case, it is, and we're happy that it can do the job. And after you plot the frequency response of this filter and you compute the errors, let's zoom in here, what we find is that this is the approximation error. That means the deviation from number 1 in the pass band, which is 0 to 0.4 pi, and the deviation from 0 in the stop band, which is 0.6 pi to pi. This is the big frequency response, magnitude of frequency response. Here there's a bit of ripple, and here there's a bit of ripple. In the log scale, you see the ripples are here a lot more than the other. But when you look at the approximation error, which is the dB here is 0, which means the amplitude here is near 1, and here the amplitude is close to 0, right? So if you look at it in non-log scale and just say, let me subtract the amplitude of my filter from 1 in this band, I get this. Let me subtract the amplitude of my filter in the stop band from 0, I get this. So this is my approximation error. And in case you can't read the labels, this number here is minus 0.001, and number here is 0.001. So we're almost satisfying the specs, but not quite. Why? Because these things actually touch, this one actually touches this. It goes a little bit below 0.001. So if you're really strict about your spec and you really want it to remain within 0.001, you can increase the number of taps from 38 to 39, and that would more or less do the job. Now if I increase the number of taps from 38 to 39, I end up being what? Type 1 filter again, right? Because that has odd number of taps. But is that a problem? No, because type 1 can also be a low-pass filter. However, if I went through the same design methodology here for a high-pass filter, and I won't do it in class now, but it is in the book, what you find is that every time you do, so let me backtrack just a little bit. So in this whole design process, it was a little bit of a trial and error, if you will. In what sense? These formulas are all approximate. Not only do I not have control over the ripple in the passband and stop band being different from each other, I designed something and it didn't satisfy my spec. And why is that? Well, because it's a window design technique and it's a bit of a trial and error. And that's why we study FIR optimum filter design in just 5 minutes or 10 minutes from now. But if we were going to design a high-pass filter, and this business of, it didn't satisfy the spec, let's just increment n, the number of taps, by 1 to see whether that does the job or not. You could do that, but you have to make sure that the new type of filter that you end up getting doesn't contradict, can in fact accomplish the type of the class of filter you want to design. So if you end up designing, if you let beta equals 0 and you end up designing a type 2 low-pass filter, a type 2 high-pass filter, then you know you're in trouble because type 2s cannot be high-pass. So then you have to maybe increment by 2 in order to get away from those impossible situations, right? Remember, we have that table that tells you type 1 filter can be any low-pass, high-pass, band-pass stuff. Type 2 cannot be high-pass. So if you get stuck into those situations, you have to improvise using this technique and increase the number of taps just a little bit more to get around those. Okay, are there any questions or comments regarding this? Actually, just one more thing before I forget, I'll get the question in just a second. Another confusing thing that I found, questions that I got was this sort of a linear phase relationship, and I realized I might not have stated this explicitly. It turns out if the ideal filter that you start off with, H sub d of n, which is like the sink, for example, right? if that's linear phase, and the window that you design is also linear phase, when you multiply those two things by each other, you get a final linear phase filter. That I never explicitly mentioned that. I wasn't in my notes either, so I'm going to state that a little bit more formally from this year on. But the reason we got all this linear phase stuff working nicely here is because we start off with a linear phase filter that's the desired response, and then we multiply by window that's linear phase. And why is it that the windows are all linear phase? They're all symmetric, right? So they're easy to satisfy the linear phase condition, and therefore the final filter we get is also linear phase. Yeah.
Why does beta have to be an integer?
Because it has to do with the definition. Because you have a quantity, I think the answer is because you have a quantity like I naught of beta prime, and probably zeroth order modified Bessel function is defined for integers. That would be my guess. Let's see, and here you have I naught of, hold on, beta times. So if this is an integer, then this is an integer. Well, should the argument for I naught be can it be a non-integer? It would seem to me, based on this definition, it could, right? Yeah, I think my guess is that my initial gut reaction would have been to say that here, this n for nth order modified Bessel function, that has to be an integer, right? It's 0, 1, 2, etc. Yeah. Perhaps computing this is more difficult for non-integer values than it is for integer values. That would be my guess. Although if you have this series expansion, I can see that you can put any x you want it. Yeah, that's a good point. I mean, certainly the value of w of n is not integer, but somehow it must be that is yeah. Right now, I'm off the top of my head, I would say it could be non-integer, but let me look into it a little bit more. Let me make sure 100% that there's no problem with this argument of I not being an integer. Has anybody used these modified Bessel functions? Is there any problems, or are they extra hard to come? I know that in the CRC book, for example, is the place you look up the values of these Bessel functions, and I know on those you have them for integer values. So maybe it's a legacy. Absolutely. I mean, if I look at this series, x can be anything. There is no limitation why it should be integer or non-integer. So, yeah, I think it could be. It could be. Let me see. Look at here. Yeah, it could come out of this thing as well. Well, certainly m has to be integer. There's no way to get around that. Yeah. Yeah, actually, off the top of my head, I don't see any reason why beta has to be an integer. That's a good point. M definitely has to be an integer, but not necessarily beta. That's a good point. It could. One of the things that might have happened is that if you plug it into this, you see, when you plug into this equation, there's no guarantee m is an integer. So certainly if m ends up being a floating point number, you have to integerize it. No question about that. But I think beta prime can be just about anything. I don't see why it can't be an arbitrary number. Okay. Okay. So at the end of the day, you know, you compute m to be 30. M is 38 right off the equations. It doesn't satisfy, so you increase that to become 39. So that gives you a new W of n. Now that you got your value of your M and you got the value of your beta prime, you come back, you plug it into this formula, and that gives you your W of n. And then once you have your W of n, you multiply it by H sub D of n. But you need to know what the H sub D of n is. And what is it? It's the inverse Fourier transform of H sub D of omega. And what is H sub D of omega? Well, we know its magnitude. And what's e to the j beta and e to the j alpha? Where alpha is the same alpha as coming off of your Kaiser window, which is 2 times alpha is m. And beta, we already picked it ahead of time to be equal to 0, so to limit ourselves to type 1 or type 2. Okay? So you need to know the entire expression for H sub D of omega to compute H sub D of n, so that you can then multiply by W of n, so that you can get the final filter H of n you're interested in. So somehow ahead of time you got to make a choice whether you're going to do type 1, type 2, or type 3, type 4. Type 1, type 2, beta is equal to 0. Type 3, type 4, it's the other kind. Okay. And generally speaking, type 1, type 2 is a safer bet. Why? The two of them together cover a wider range of classes of filters than type 3, type 4 does. Right? Type 1 in particular can do any class of filters. Okay. Are there any other questions? Okay, so I'd like to switch gears. Again, I'd encourage you to read the high-pass example in Oppenheim and Schaefer to get an idea of a case where, again, increasing the number of taps doesn't really do the job. Any other questions or comments? Okay, so far we talked about FR filter design using Windows, and we saw at least two negative points or two bad things about designing Windows. One is you go through all the trouble and you're not necessarily guaranteed the thing will satisfy your specs. And two, there's no way of differentiating between the ripple in the stop band and pass band. And what's a bad consequence of that? Whereas the spec, in that last example, whereas the spec was that in passband the ripple should be 0.01, we ended up designing a filter with the final condition that the ripple in the passband was smaller, was 0.001 instead of 0.01. And how does that manifest itself? So we satisfied the spec, but in some sense we over-satisfied the spec, right? And why is that good or bad? I mean, some of you might say, that's great, you know, we're better than what they asked us to be. And it is true, we're better, we ended up designing a filter that was better than what we got asked to design, but it's not all rosy like that. What's the drawback? What was that at the expense of? Yeah.
Number of taps.
Yeah. There's no free lunch. If you over-satisfy the specs, it probably means your filter had more taps than necessary. And you don't want to have more taps, because if you can get away with a 5-tap filter, why have a 17-tap filter? You end up doing 3 times more computation having a 17-tap filter than a 5-tap filter. So there is a general interest in designing the bare minimum number of tap filters to do the job. It's not just a minimalist approach, it's desired. It consumes less power, it consumes less CPU, etc. And so that's really the main fundamental drawback of window design using FR filter design using window technique. It's intuitive, it's easy to understand, it's fast, it's quick, and you're probably going to design some by Friday for your homework. But the drawback is that it's not guaranteed to result in the lowest number of taps satisfying those set of specs. So as a result, as I said earlier, in 1975 or so, Jim McClellan, who was a PhD student at Rice doing his thesis with Tom Parks, came up with a new filter design technique called optimal filter design. And optimal filter design actually is a technique that takes a little bit more than a lecture to cover. And since we're already somewhat through the first half of this lecture, I will start it today, but I'll finish it up on Friday. And before we even get to talk about optimal filter design, I'm going to lay the groundwork by talking about some observations regarding FIR filters with linear phase and all that. So to begin with, it's going to be a little bit of a observation type thing. Okay. So let's talk about. Could you bring the camera? Yeah, great, and move it that way. Great, thank you. So let's talk about optimal FIR filter design. So I'm going to limit our discussion to type 1 filters because they can implement any kind of filter, but the argument can be repeated for any kind. So we want to talk about type 1 generalized linear phase filter. And again, I'm going to, for the sake of this argument, I'm going to concentrate on low-pass filter, but this argument can be generalized to high-pass and other ones as well. So if I rewrite the expression for h of omega, it's h sub m of omega, and for this particular case, times e to the j beta, e to the minus j alpha omega. This is a generalized low-pass, generalized linear phase. And for type 1, and type 2, by the way, beta is equal to 0, and also n, the number of taps, is odd. Okay? And furthermore, we know that there's this symmetry, h of n is equal to h of capital N minus n minus 1. That's what type 1 filter was all about. Okay? And I think it's part of your homework assignment that you're going to be doing by Friday, but another derivation of this type 1 thing was that h sub m of omega takes on the following form. If n is the number of taps and it's odd and it's equal to 2m plus 1, it takes on the value n equals 0 to m of a of n with some coefficients cosine omega n, where these a guys are related to h in the following way. A of 0 is equal to h of 0, and a of n is equal to h of m minus n for all other n. Okay? So this is pretty much a review of what we know about type 1 linearized, type 1 generalized linear phase, right? And I'm going to be, so these coefficients A are related to coefficients H of the original filter. This guy has impulse response of H of n, right? I'm going to refer to this H sub m of omega by definition. I'm going to call it G of omega. And I'm going to spend the rest of the lecture today making observations about G of omega. So observations on G of omega. First of all, the observation number 1 is that G of omega is a continuous function of omega, and it's as many times differentiable as you want. And you might just say, why is she making these observations? You really have to wait till the end of today's lecture, end of Friday's filter. We're going to use these observations at the correct moment. So rather than take a detour in the middle of the actual derivations, let's come up with a set of observations, and then we'll use these in just a minute or in just an hour. So first of all, G of omega is a continuous function of omega and is as many times differentiable as you want. Okay? And why is that true? Because it's a sum of a bunch of cosines. Cosines is a smooth function. It's differentiable. This is essentially a trigonometric polynomial, right? and we'll talk about that in a little bit more. But I mean, cosine omega n. Sorry, there's no parentheses here. Parentheses is here. Cosine omega n. Because why? Because h of omega has e to the minus j omega n together, so this is cosine omega n like that. Because so you have cosine of omega plus cosine of 2 omega plus cosine of 3 omega added up with proper scaling factor. Each one of these cosine functions, oh my god, they're infinitely differentiable, they're infinitely smooth, they're infinitely continuous. It's the most desirable functions you ever wanted to have, right? And number two, it's more like a question rather than an observation. How many local extrema does g of omega have? How many local extrema does g of omega have? And what do we mean by local extrema? What does extrema mean? Minimum or maximum? Why do I call it local? Because there's a thing called local minima, local maxima, or global minima, global maxima. A function could have lots of local extrema, but it has one global extrema. Global means it achieves maximum or minimum over the entire range of its variable. So for example, if I have a function that looks like this, this is a local minima, this is another local minima, this is another local minima, but this is a global minima because over the whole range, it never went below that. So global minimums are also local minimums, but they're more. They're more minima than other ones. The same thing with maxima, right? And how do we compute local minima or maximas? How do we compute local extremas? Yeah. In fact, that's what they teach you in calculus, is that if you set the derivative of a function equal to 0, what do you get, global or local minimas? Local. So no problem. So let me just draw that here. So this is a global minima, and this is a local. An extrema, and by the way, again, when you set the derivative of something equals 0, do you get a maxima or a minima? Both. So you don't know. So that's why I use the word extrema. So extrema can be minima or maxima. And local rather than global. So we're interested in everything. We don't necessarily want global minima. By the way, for those of you who have done function optimizations before, is it easy or hard to compute global minima? Has anybody had to program a optimization thing where they had to find the global minima of something? No more. Yeah. And so, is it easy or hard? And what would some of the challenges you had to go through?
It depends on the function. For some functions, it's easy.
Mm-hmm.
Functions convex.
Mm-hmm.
It's very easy, but if it has a lot of local, it's very hard.
Exactly. So for some functions, it's very hard to find the global minima. In fact, if you're doing numerical optimization of a function, making sure that so how do numerical optimization techniques work? Well, you have to take EE227, but just in one sentence, what EE227 is all about is you start with some initial condition, and let's say you do something very, very simple, steepest descent. You figure out which direction in this multivariable, it's most of the times it's function of multiple variables, x, y, z, and w. You have a four-dimensional function, and you ask yourself, which direction should I move so that the value of the function becomes lower? And then, oh, this direction is the best. So from where I am, I'll go down. It's almost like you're stuck in a bunch of hills, if you will. That's it. And you just keep going down on the direction that takes you down. And what does that do? That takes you to a local minima, right? If think of these as mountains, right? If I started here, and I did this strategy I implemented this strategy I just talked about, at any instant point in time, walk towards a direction that makes the function go lower. So in the one-dimensional case, I can either go up or down. I can either go to the right or to the left, right? And which way would I go if I want to minimize something? Right. I keep going right, and I hit here, and I say, "Oh, good, I'm at minima." But that's a local minima. So a lot of time, one of the big challenges when you're solving numerical optimization problems is that you get what's called stuck in local minima, and you don't want that. Many times your goal is to find a best minima, the global minima. And so what are some techniques people have come up with? A classic one is simulated annealing or genetic algorithms. And what it does, it says, even though moving right makes me go down and makes me approach a minima, I flip a coin. And sometimes I listen to what the direction that the greedy algorithm tells me, and sometimes I don't. I make a jump. I make a random jump here, 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 depending upon what's going on. And it's a probabilistic thing. And after I make those jumps, chances are, on one of the jumps, I lie down here, and after a long time, I approach the local minimum. So this is simulated annealing. It was very hot in the late 80s, and people were very excited about it, and it enabled people to find global minima. Dan, is that what, your name is Dan, right? Andy, sorry. Andy. Is that what you used? Some sort of a jumping around, simulated annealing, or?
Not exactly. I use large step sizes to
Got it.
step over the domes.
Got it. Okay, so anyway, just this is a side comment. Finding global minima is difficult, but local minima is easy. So, in order to answer that question, what we're going to do is start with this G of omega guy, which is this expression here. This is G of omega. And what we want to do is express this cosine omega n's as a sum of powers of cosine omega. So express, in order to answer this question, express cosine omega n as sum of powers of cosine of omega. So what do I mean by that? Well, cosine of 2 omega is 2 cosine squared omega minus 1. Cosine 3 omega is cosine of 2 omega plus omega, which is cosine of 2 omega cosine omega minus sine of 2 omega sine of omega, which is cosine omega 2 cosine squared omega minus 1 minus 2 sine squared omega cosine omega, which is the same as which is the same as 2 cosine cubed omega minus cosine omega minus 2 cosine omega 1 minus cosine squared omega. I'm replacing all the sine squares with 1 minus cosine squared omegas, which is the same as 2 cosine cubed omega minus cosine omega minus 2 cosine omega plus 2 cosine cube omega, which is the same as 4 cosine cube omega minus 3 cosine omega. That's the final answer. That's equal to cosine 3 omega. I can repeat that. I can write, in general, I can write cosine omega n as sum of powers of omega, cosine omega. In this same manner, cosine 4 omega is then cosine 3 omega plus omega expanded. And what do I mean, sum of powers of cosine omega? This is cosine omega to the power 1. This is cosine omega to the power of 3. This is a sum I'm making, but I'm scaling it. This gets multiplied by 3. This gets multiplied by 4. Okay? So more generally, I can do that. So in particular, I can write cosine omega n as summation from I equals 0 to n of some coefficients. I call it alpha I times cosine omega to the power of I. That's what I mean. I can write it as sum of powers of cosine omega. I was able to do that for cosine 3 omega, cosine 2 omega, etc. Okay? And if I do that, this polynomial here has a famous name. And what is it? These have a famous name. Chebyshev coefficients. Okay, these are called Chebyshev coefficients. And Chebyshev, by the way, is the same fellow as is the same guy as Chebyshev error, is the same guy as Chebyshev bound. Does anybody know what Chebyshev bound in statistics is? Yeah.
I guess it's a bound on probability of random variables in the algorithm.
Right.
Expectation.
Right, as n tends to infinity, as the sum of it tends. So this guy Chebyshev, which by the way his name has multiple spellings. You can spell this last V, can be sometimes F, sometimes the T is not there, sometimes the B is V. We don't have any Russian-speaking people here, do we? Or Russian origin? We don't. But in the past years, they've always reminded me what the correct spelling is. But anyway, so these are Chebyshev coefficients, and these are called Chebyshev polynomials. Okay, but the thing to remember is that cosine omega n can be written as a polynomial in cosine omega. Why is it a polynomial? It has powers and it has coefficients. So in particular, I can write g of omega also because g of omega itself is a polynomial in cosine omega n. Now, if I now let me not jump too many steps at once, but this is our definition of g of omega, which is the summation from n equals 0 to m of a of n. And now instead of cosine omega n, I put this blah here, which is I equals 0 to n alpha I cosine omega to the power of I, right? So then I can combine these two things, and I plugged in, instead of cosine omega n, I plugged in this value here. And so now I can say g of omega is just a summation. So this is the coefficients of this guy, and this is the coefficients of this guy. I can combine it all in one gigantic thing, and I get, what do I get? I get a polynomial in cosine omega again, right? And what's the degree of that polynomial, do you think? Well, if I stare here, the largest value I would get here would be cosine omega capital M, right? And so the largest thing that this would get would be what? So I can write this as summation from n equals 0 to m of some new set of coefficients gamma, and then cosine omega to the power of n, right? Because this gives me yet another polynomial, and the maximum order of that polynomial for cosine omega is n, right? It's little n because this summation goes to little n. So I'm going to have the highest power cosine omega term I'm going to have is cosine omega to the power of n. And so that's it. And now this little n goes from 0 to m, and so it gives me a high-powered polynomial as in terms of cosine omega. And this gamma encapsulates what? Encapsulates these a's, alpha i's, all of those gets jumbled up and bundled up in one thing that I call gamma. And how the two things are related, oh, it's a messy thing, and God help anybody who wants to do that, but let's not worry about that. I'm not worried about that relationship. I wanted to show some properties of that because we're going to need those properties in just a second. So now that I wrote g of omega in this term, what can I say about its number of local extrema? How do I compute that? Is it too easy? Just take the derivative, right? So to compute local extrema, take derivative and set it equal to 0. This is like from calculus 1 or something. So d omega is equal to 0. That means the summation from n equals, now I'm going to take the derivative of that, and derivative and summation can be interchanged. I can bring the derivative inside. This thing is not a function of omega, so I just take the derivative of that. So gamma of n, what's the derivative of that with respect to omega? It's n cosine omega n to the minus 1. And then chain rule, the derivative of cosine omega is minus sine omega. Set that equal to 0. And so what do we have? So how do we then find out how many local extrema does it have? Well, to find out the answer, well, there's two things here. There's this term and there's that term, and sine of omega can be taken out, right? So that means if I were to rewrite it, minus sine of omega times n equals 0 to m gamma of n cosine omega n minus 1 is equal to 0. So there's two solutions. Solution one is sine omega equals 0. That means omega equals 0 or pi. Or this other summation is equal to 0. N equals 0 to m gamma of n cosine of omega n minus 1 is equal to 0. Yes, thank you. This n got dropped here. Thank you. Okay? So what can we say about the roots of this polynomial? What's the maximum number of roots the thing could have ever? Well, this is a polynomial in cosine omega. That means I can think of cosine omega as just a variable x. Okay? So what can we say? What, this is a polynomial of order what then? M minus 1. And a polynomial of order m minus 1, how many zeros can it have? Right? So this can have a maximum of m minus 1 zeros. And a polynomial of order m minus 1 in general has what? Real or complex zeros? It has real coefficients. That's right. It could have real or complex conjugate, right? And you might come and argue with me saying that, okay, if you replace cosine omega with x, now you have a polynomial in x, and the roots of that polynomial in x could be real or complex. Now, let's say I get a complex conjugate pair or some complex number as the root, then what value of omega do I pick? Cosine omega equals a complex conjugate number? What omega would that be? A complex omega, but we're not interested in that for the sake of this argument. We're only interested in real omegas, but just in case, I'm talking about maximum number of zeros, so at most this thing have m minus 1. There could be m minus 1 real values of omega that make this guy 0. Again, I'm interested in maximums. Okay? So putting these two things together, what can I conclude? I can say the total number of local extrema is this plus that, is an m minus 1 plus 2, which is m plus 1. I'm going to put that in a box. Okay.
What if you get one of the absolute value greater than 1?
It's also a complex conjugate omega. But for now, the question that I started off with is this. How many local extrema can this guy have? And it can have max m plus 1. Okay? So having made that observation, I'm now ready to embark upon FR filter design, and and I won't finish it today, but I think we should at least start it. So let's start with problem statement. So I'm gonna start with a series of problems, problem A, and then I'll do what typically mathematicians do, which is reduce solving problem A to problem B, and then I show you if I can solve problem. If I can find a way to solve problem B, I've essentially solved problem A. Then I reduce that to problem C. If I can find a way to solve problem C, I've effectively solved B. And then finally I solve C, and that's the end of the chain. Okay. So the problem I'm interested in is this, right? I've been given a set of specs, h of omega, and again we're dealing with low pass, but we can be anything. The ripple in pass band is omega p, the ripple in stop band is omega s. Look, I'm calling it omega 1 and omega 2, sorry, change of notation. And it's the good old specs from a low-pass filter, so I'm given omega s, omega p, delta 1, and delta 2, determine coefficients of g of omega. What I mean is those a of n values, such that what happens? Why would we embark upon this problem statement for optimal FIR filter design? Why did we embark? What do we mean by optimality? What is minimized? Such that what's minimized? Number of taps. M is minimized. And why am I caring about A of n or not H of n? Well, A of n and H of n are related in this way, so if I just find A, I've effectively found H. Okay, and why am I caring about G of omega, not H of omega? Well, the magnitude of H of omega and G of omega based on this relationship here are all the same thing, right? So that's the problem I'm fundamentally interested in. And now I'm going to transform that into problem B. I go on to a new page. We all agree this is the thing we want to solve, right? We want to minimize the number of taps. So problem B is this. It goes, given omega p, omega s, m, and k, which is the ratio between delta 1 and delta 2, determine A of n such that delta 2 is minimized. And I claim that problem A and B are equivalent to each other. In other words, so let me draw the box for that. So here the input to this is omega p, omega s, k, which is delta 1 over delta 2, and m. This is algorithm B. And outcomes A of n and delta of 2. So what I call this algorithm B, and what I want to show is that indeed, if I came up with a box that did accomplish this, that given those inputs, it would give me A of n such that delta of 2 is minimized. If I had a box like that, it's hypothetical, then I can use this box to solve problem A. And what was problem A? I had a box with all of these, but we wanted to find A of n such that m is minimized. This thing, we're trying to minimize delta 2. So what my goal is to show that if I had a box, I call it algo B box, and then I can use it to solve problem A. And it's coming up with showing this is pretty straightforward. How do you do it? Well, it's just a simple iterative step, and let me show you how you go about doing it. So you start with omega p, omega s, delta 1, delta 2. You're given all of that, so this is problem A. From here, you compute k, which is the ratio between the two deltas, delta 1 over delta 2. And then you also guess some value for m, which is the number of taps of the filter. And now, I can plug all of these things into the algo B box, right? Because that's how algo B works. It takes these inputs and produces it produces a set of coefficients A prime and a corresponding delta 2 prime. Okay? So we start out with given these quantities. And then you ask yourself, is the resulting delta 2 prime smaller than delta 2? So it's a if box, if you will. Is delta 2 prime smaller than delta 2? There's a yes and there's a no. If delta 2 prime is smaller than delta 2, what can you say? What would you conclude about the value of m that you guessed? It's bad. What does bad mean? Is it too large or too small, or what is it? If delta 2 prime is smaller than delta 2, that means we oversatisfied the spec. That's an overkill. And if it is an overkill, how do we undo that situation of overkill? We reduce m by 1. And then come back and repeat this process. if delta 2 prime is not smaller than delta 2 and it's in fact larger than delta 2, what does that mean? This was our original specs. We had to satisfy the delta 2 spec. So if the resulting ripple that we get is larger than what we wanted to, we didn't satisfy the spec. So what do we do to M? So increase it by 1. And then come back here. And so you keep doing these loops until you find a set of coefficients that if you decrease M by 1, it won't satisfy the spec, and it's just the right value. Okay? So this iterative flowchart that I've sort of drawn here shows you a way that, you know, if you did have a box, algorithm B box, that would take these inputs and would generate AN such that delta 2 is minimized, if you had that box, you plugged it into this, you've effectively solved this problem. Right? So I've reduced the original problem into another problem. And why did I reduce that? Well, hopefully this new problem is a little bit easier to solve. This is not an integer optimization problem. It's more like a real optimization problem. And what I'll show you next time is I reduce problem B to yet another problem. It's called problem C. And then what you'll see is that we solve problem C by using what's called alternation theorem from approximation theory, which is really just a field in mathematics, to solve problem C and therefore this problem. And just as a side comment, a lot of problems in signal processing have roots or relationships with this branch of mathematics called approximation theory, because you're trying to come up with functions that approximate some other given desired thing, right? So in fact, when you design IIR filters with rational transfer function, then it relates to what's called rational approximation theory, rational function approximation theory. So there's a lot of one-to-one correspondence between filter design ideas and signal processing and approximation theory. Moreover, when you talk about signal representation techniques like wavelets and those other things, that's another aspect of approximation theory in mathematics. So because you're worried about representing signals and representing filters and stuff like that, approximation theory a lot of times comes to your rescue. And what Parkes and McClellan did, or in particular what McClellan did for his thesis, was he was so clever, he found out that these results that mathematicians had discovered many years ago in approximation theory is smack on applicable to this filter design problem. So he's the guy who recognized that. The same way as, you know, when we talk about FFT, Cooley and Tukey at IBM in 1963 were the guys who recognized that Gauss's algorithm from 200 years ago is applicable to doing FFTs. It has always been sitting there, but the computers weren't there, the machinery wasn't there to make that useful. But suddenly there comes a time where you realize, boy, you know, we could use those results. So that pattern happens a lot in signal processing, where some result from mathematics either gets invented. Wavelets actually more or less got invented in the 90s. So they haven't been around that long. At least 10, 15 minutes to explain. So we'll pick up this discussion on Friday. And so just one quick announcement. Dan, what do you want these guys to hand in on Friday? Everything hard copy handed in here? Okay. Including your MATLAB functions, right? Yeah. Okay.
the gain, the low frequency gain of this stage, A0, which is this point right here, is equal to GM R out.